So they say they found microplastics in our blood. This was reported by The Guardian, and the article is fairly short. The main message is that scientists found the tiny particles in almost 80% of the people tested. These were people who volunteered and provided blood samples. And the rest of this is just kind of boilerplate information about plastics, and then some quotes by one of the authors about how important their work is and how they need more funding and that kind of thing. So, as a scientist, I don't just believe everything I see in the popular literature, and I wanted to read this scientific article, and because it was reported so broadly, I assumed that they would have very solid evidence backing up this finding. So let's take a look at the article. Here it is. It's published in Environment International 2022, so it's a couple years old now. Real quick, let's just check. Here they report 77% of the donors, 17 out of 22, had a quantifiable greater than LOQ. We'll talk about that. Massive plastic particles in their blood. So 77 is close to 80, so the Guardian is correct in their reporting according to what's reported here. Let's go straight to the results because it's all very well summarized in this figure 1. This is a capsule summary of all of the testing that they did of the 22 blood samples. Most of them were done in duplicate. So they have both A and B samples that they tested for most of the donors. So that's what you see along the x-axis is the sample. And you can see 1A, 1B, 2A, 2B. So 1 is donor number 1, A and B are duplicates. And then you see the concentration of the plastics, the microplastics in micrograms per milliliters of blood. That's more or less parts per million. And if you look, just glance at this, you say, okay, well, there's a lot of big bars on that chart. I guess they did find a lot of microplastics when they were looking in the blood. But if you look a little bit closer at this data, some things are a little troubling. So let's take a little closer look. This is the exact same figure that we were just looking at. I just took a picture of it from the article and put it into PowerPoint so we could break it down a little bit more. So let's start with samples 1A and 1B. The interesting thing about samples 1A and 1B is that they're not the same. Now these are duplicates, so they came from the same donor and they should have the same number. But you see in this case there's PET, which is polyethylene terephthalate, which is essentially polyester. It could be from a drinks bottle, it could be from polyester in fabric. And they found that in one of the two samples, but not in the other. So that's kind of strange. You would expect those two bars to be the same. Well, then you look at 2A, it's the same thing. You've got PET in one, not in the other. You go to 3, now you've got polyethylene and PET in one, but not in the other. And amazingly, you keep going through this chart. 4, A and B, not the same. 5, 6, there was only one sample. There's no duplicate. But then 7, also not reproduced. 8, not reproduced. 10, not reproduced. 11, okay, you look and you say, well, 11, 12, and 13, there's polystyrene in both of them, but there are big differences between the A and the B samples still. We'll come back to that a little bit later. And then you go 14, 16, 17, 19. None of these that have duplicate measurements have the same measurement for the A and the B samples. In fact, the only ones where the A and the B samples match are 20, 21, and 22, where you have no microplastics found in either sample. So this is really bizarre. So these are all what's above limit of quantification, which we'll talk about a little bit later. But regardless of what that cutoff is, if you have your true concentration above that cutoff, then both of the samples should show a measurement over 50% of the time, even with any amount of variation in the sample. If the true concentration is below, then you should get a 0 in this case because of the cutoff, but you should get both of them at 0 over 50% of the time. Now, at most, if your true concentration is right at the limit of quantification, so right at that cutoff, you would get a positive and a negative answer about 50% of the time. So the most you should get this sort of non-duplication of results is if the number happens to be right at the cutoff, and then you should only get it at most 50% of the time. So these results are really odd, and I decided to take a closer look at the article to see if the authors said anything more about them. So I looked through the article, and this is the primary message that they had to say about why they get such low reproducibility of their measurements. And they basically say that if you include the numbers that are between the limit of detection and the limit of quantification, so just below the cutoff value for limit of quantification, then they show better agreement. Okay, so essentially, if you include noisier data, then you get more better agreement. Let's talk a little bit more about what these numbers mean, this LOD and LOQ, because I think this argument doesn't really make sense if we don't understand what those are. So let's go to that. They have a nice summary here where they say, okay, if it's less than limit of detection, less than LOD, then they don't know how much it is. It's between 0 and the LOD. Now, every analytical method has a limit of detection. If you're below the limit of detection, you just don't know. There may be some in there. It's just you're not able to detect it with this method. Okay, that's normal. But they put the limit of quantification at a higher threshold. So they say in some cases we can see evidence for some microplastic, but we don't really trust the quantification of that value unless it gets above limit of quantification, this LOQ. So they set a higher bar, a higher standard for the numbers that they want to quantify and give a number for and list in the chart. This is a fairly common way to make sure that you only report numbers that are reliable. So that's fine. Now, what they're saying is that by some fluke, a lot of their data have numbers that are between LOD and LOQ, so they don't show up in their figure. And that's why it looks like their numbers are not reproducible. Let's take a look at those numbers and see what we see. Here they are. These are the numbers. This is from their supplementary material. So this is also available online for anyone who wants it. There's no paywall or anything for the article or the supplementary material. You can go and find this and look at it to your heart's content. So you see, again, they list the donor, they list the plastic type, and then if it lists less than this means less than the limit of detection. So in the case of PMMA, the limit of detection is 0.093. They don't see any in 1A or 1B. The more interesting ones are the ones with an asterisk. Okay, those are the ones between LOD and LOQ, so between limit of detection and limit of quantification. And then the ones that are just a number like this 0.97 here for PET in 1A, that is above the limit of quantification, and that appears in their figure. So what they're saying is that there are a lot of examples where the numbers above LOQ and the number between LOD and LOQ are similar. And they may have even listed 1A and 1B as an example. That's one of the few where they're even remotely similar. There are a lot where they're just completely different. So here's 0.6, and this one is less than limit of detection. It's not even detected. Here's a 2.1, and this one is not even detected. So I looked through this whole chart full of this whole table full of numbers, and what they had described in the text didn't really seem to match up with what I saw here. I really couldn't find a way to make this data look reliable or reproducible at all. So let's look at a little better summary of this data rather than trying to look through each of these squares one at a time. So what you can do is you can plot these data. So you plot the A value on the x-axis and the B value on the y-axis. If the numbers are the same, obviously, then they should fall along a straight line with a slope of 1, an intercept of 0, and a goodness of fit close to 1. Now, in reality, of course, your slope may vary from 1 a little bit, your intercept may vary from 0 a bit, and your goodness of fit is going to be less than 1 with real data. But it should be something close to this, okay? So let's see what we've got. Okay, so these are their data from that previous table that are summarized in this chart. So this is their data for polystyrene, where you have the A values on the x-axis, B values on the y-axis, and you see a slope here of 0.1 and an intercept of 0.6, a goodness of fit, which is terrible. Okay, a slope of 0.1 is much closer to a slope of 0 than 1. A slope of 0 means there's 0 correlation. That means there's no correlation at all. It's essentially as if you picked random numbers out of a hat. So this is much closer to no correlation than a good correlation. Polyethylene is even worse. It's almost exactly a slope of 0. So once again, there's no correlation between the A and the B samples, which should be identical. They should fall along this line. And then the data for polyethylene terephthalate for polyester is also very bad. It's also, the slope is very close to 1, very close to 0, not close to 1 at all. In fact, this one's slightly negative. But what this really means is that there's no correlation between the A and the B samples. And what that means, you don't have to be a scientist to know what that means. If you measure something and you try to measure the exact same thing again and you get a different number, then you know something's wrong. And when you do it 17 times in a row, even more than that if you break it down by polymer type, and you essentially never get the same number or maybe only occasionally by accident, then there's something wrong with the method. There's some sort of a systematic problem with the measurement or the data. And when you see a plot like this, which happens, I mean, this kind of thing happens when you're developing a method and you haven't got it figured out yet. You may see data like this, and a popular joke when you're at this stage of development is, all I have right now is a random number generator, right? I don't really have an analytical method. It's just giving me random numbers. And with respect to A and B values, it is a random number generator, but these are actually not random numbers. Let's take another look at that plot, because there's something else going on there that I want to point out to you. So while there's no agreement between the A and the B samples, what's interesting is there is a pattern among neighbors. So if you look at 1A, 2A, 3A, 4A, all of those have green. All of those have polyester in them. Okay, so there's this trend, there's this pattern from 1A to all the way up to 10A of some polyethylene terephthalate in those. And then there's another pattern with polystyrene and polyethylene, the yellow and the blue, that goes from 9 through 13. And then there's another pattern for polystyrene, which goes in the B samples from 11 through 19. And that's quite easy to see if you just plot the data a little different way. And this is the way that you can look at it to see that even more clearly. So again, this is the same data. I just changed the x-axis now. Instead of putting the 1A and 1B samples next to each other, I lined this up the way perhaps a sample vial container might hold sample vials as they're being stored, as they're being prepared, as they're awaiting analysis, or there's something else happening to them. And so you can see this neighbor effect very clearly now. So it's pretty easy to look at that 1 to 10A and just say, maybe a little bit of polyester dust that might have been in the room or might have, slipped off of the sleeve of one of the analysts. It just sprinkled into that area of the samples, right? And then it's the same thing for, 9 through 13 with polystyrene, polyethylene. And then again, in the B samples, there was some polystyrene that got sprinkled into those. And now you see why it just happens that there was some little bit of agreement in the polystyrene is because there's two separate regions of polystyrene contamination in the 9 through 13 for A's, and that overlaps with 11 and 13 in the B's. So that really wasn't even an agreement. That was just a coincidental overlap of this pattern of external contamination. So that's what you have. There's no evidence of microplastics in blood that's presented in this paper. The pattern is very clear that it's contamination. And so let's go back to the article one more time because I just want to show you one more thing. Okay, so this is a live look at the article online, and this has been cited and it continues to be cited both in the scientific literature and the popular literature as evidence of microplastics in our blood, right? So this is being used as scientific evidence. Policy citations 53, so there are people making policies based on this. Over 2,000 readers, over 900 blog mentions, over 2,200 shares, right? So this is really making the rounds, and those kinds of metrics are really good for an author, right? I mean, this looks good on a resume to have an article that's this popular, that gets cited this often. And so there's really very little incentive for them to retract the article, which is what should happen. And there's, of course, very little incentive for The Guardian or any other popular news source to retract their articles because they still have plausible deniability. This scientific paper is still out there. And I know that there's a school of thought that says, you know what, who cares? We know plastics are terrible. There are a lot of other studies that show how bad they are. And if this just contributes to the cause of getting plastics out of our water, air, and land faster, then I don't care that it's wrong. Well, okay, I have a lot of problems with that. One is, well, first of all, you're free to hate plastic, okay? And if you want to make your purchasing decisions, you want to make your lifestyle choices based on a distaste for plastic, you're perfectly free to do that. If you want to write an editorial or you want to write to your congressman or your newspaper or whatever, a blog about how bad plastic is, of course you're free to do that. But that kind of thing does not belong in the scientific literature, okay? The scientific literature is sort of the last anchor we have for truth. And there are plenty of sources for misinformation already. And to see this kind of start infiltrating into the scientific literature is very concerning because this is sort of our last place of refuge for the truth. So the scientific literature should be about data, what the data says, and your conclusion should be supported by your data. And in this case, not only are the conclusions not supported by the data, they're refuted by the data. The data itself points out that the conclusions of microplastics in blood is absolutely incorrect for this study. And they did such a beautiful study. I mean, they have duplicate analyses, which is about the only paper of this kind that does that. And so the data are very clear. They very clearly indicate what's going on. But these authors just chose to ignore the data. And they reported the conclusion that they wanted to find. And I think that's really the issue. They started with the conclusion, right? They started with the conclusion that there's microplastics in our blood. They did some experiments. Some of them showed some indication of microplastic, and they just turned their brains off, and they went running to publish this stuff, both in the scientific and open literature, and didn't stop to consider that there was another explanation. And that's just not science. That's not the way science works. So this should have been a cautionary tale for other people. What the real message of these data is that it's very difficult, even when you take all kinds of measures, which these scientists did. They took a lot of measures to avoid contamination from the environment. But even when you take all of those measures, there's still a chance that you're going to get some microplastics in from the environment. Microplastics is really a fancy name for lint and dust. I mean, it's little tiny particles of plastic that are floating around in the air, that are collecting on a bench top or a desktop, that are adhering to your clothes, that are being shed from your clothes. It's really, really hard to get rid of all the dust, right? So this is not surprising at all that they have this contamination. It's a little disconcerting that they didn't notice it. It's sad to me that the peer reviewers didn't notice it. I mean, 17 out of 17 data completely not reproduced. I mean, that should have been caught. And it's really disconcerting to me when I wrote a letter to the editor about this, how much attention was paid to my background as an industrial researcher, and how no attention was ever paid to the fact that their data in this case are just absolute garbage. I mean, there's just no support for their conclusions. So this really doesn't belong in the literature, and unfortunately, it's almost been taken as a recipe for success. And if you look at a lot of the subsequent articles, which we will do, they've kind of taken this same approach where they start with a conclusion, they do just enough measurements to get some data that could possibly support their conclusion, and they just run with it. They stop thinking about any alternative explanations. They send it out to the literature and they claim success, and it's worked for them. And the peer reviewers aren't slowing this down. The editors aren't slowing this down. I don't see anyone else speaking up. And so that's why I'm making these videos. I don't really like making these videos. I would much prefer the authors to do their job properly, the peer reviewers to do their job properly, and the editors to do their job properly. But that's just not happening. And so I hope soon I will stop making these videos. But until I start seeing, a few more reliable papers in this area, I'm going to speak up because this is really important to me. Thanks for watching. There's more to come.